Oh, good morning, Physics 30s. Mr. Thompson here. Happy Monday. All right, we're looking on page 90 of the workbook. Let's finish off Unit 4 on EMR. We've got diffraction, interference, and polarization of light. Oh, let's start with diffraction. So only waves exhibit diffraction, not particles. So when waves go through an opening or around a corner, they bend. The bending is called diffraction. The longer the wavelength of the incident waves, the more bending takes place. So around a corner, short wavelength, you have less bending here around the obstacle or corner, and here you have a longer wavelength and more bending as diffraction occurs. Through openings, the smaller the opening, the greater the diffraction. So with a larger opening, right, fairly nearly straight, just curved on the edges here. A narrow opening, there's significant diffraction, and a narrow opening with a shorter wavelength, there's less diffraction, that means less bending. Okay? All right, interference. So waves only exhibit interference. Particles do not. Waves can pass right through each other. However, when they occupy the same position, superposed, they interfere with each other. The principle of superposition. The resultant displacement of a particle is equal to the sum of its separate displacements. So two types of interference. Remember physics 20 here, right? Constructive interference, right? Either they're both positive, like crests, or they're both negative, like troughs. They add to a higher amplitude or brighter light wave in terms of light. So crest meets crest, larger overall crest, trough meets trough, larger overall trough, and of course destructive interference. So one's upright or upside, sorry, right side up, and then one's upside down. It produces a smaller amplitude. So you have a large crest, meaning a small trough, making a smaller overall crest, and a small crest with a small trough, no wave at all. Destructive interference, so the waves cancel for a brief moment of time. Okay, let's look at double slit interference, Young's double slit experiment. So page 91. Again, this only applies to waves. When a monochromatic wave, so a wave of only one color, a wave undergoing SHM, a wave of one frequency, so one color, passes through two adjacent narrow slits, there's diffraction and interference on the opposite side. When a screen is placed beyond the barrier, we observe bright dots, lines on the screen. So you can see here, right, you have essentially these two slits where light, the incident wave fronts, are passing through. This makes these two point sources, okay, producing the waves that continue past the double slit. You have points where you have constructive interference, so two crests and two troughs, and you have points that have a crest and a trough meaning, so destructive interference. That makes these bright dots here that occur on a screen far ahead. Of course, the most prominent dot's the one in the center, and then smaller dots to the left and right. So this is a bright dot or line. The difference in the distance from the two slits is a multiple of the wavelength, so the waves arrive in phase and undergo constructive interference. That's for the maxima and the minima here. This is a dark region. The difference in the distances from the two slits is a multiple of 1/2 lambda, so the waves arrive out of phase and undergo destructive interference. Okay, the mathematics of Young's double slit. So we have the following. We have sources, S1 and S2. They're separated by a distance, lowercase d. These sources are a certain distance L from a fixed screen. Notice here where you have a central maximum, okay, and then where you have maximums that are orders away from that center maximum. So max x1, okay, max 1 at 1, max 2, and then of course in between the two, min 1, min 2. The angle of deviation from this line directly between the two sources to the screen, okay, a perpendicular, that angle, right, refers to the maximums or minimums, as the case may be. The equations here, lambda equals d sine theta over n, where tan of theta is x over L because, right, the angle here, x is the opposite side, L is the adjacent side, opposite over adjacent makes tangent. And then, of course, lambda equals dx over nl, where, of course, the angle must be less than 10 degrees. Thank you for your patience. Okay, So this is the general form of the equation that works with all cases, and this is the special form of the equation if lambda is very small. Okay? All right, dispersion of light, EMR, using prisms and diffraction grating. Okay, so when light is shown through a triangular prism or diffraction grating, the different wavelengths of light bend by different amounts. This causes the light to separate into its different wavelengths, which is called dispersion. So light going through a prism, okay, or a diffraction grating. Dispersion using a triangular prism. This is for waves only once again. So when light passes through a triangular prism, the different wavelengths of light refract by different amounts. Of course, light passing through a prism spreads out into the spectrum. Red refracts the least and violet refracts the most. It says here, the shorter the wavelength, the greater the angle of refraction. So when light disperses into its component wavelengths, all wavelengths are observed with no gaps between them. We call this a continuous spectrum shown here. Dispersion using diffraction grating. Again, only applies to waves. Diffraction grating is a transparent glass or plastic that has many fine wires within it, all parallel to each other by a very small distance in micrometers apart from each other. This results in many small slits all side by side. When light passes through the diffraction grating, the light behaves much like a double-slit experiment. Each wavelength of light will have a maxima and minima shown on the screen. The location of the maxima are given by these equations that we saw on the bottom of the previous page, page 91. Based on the first equation, it follows that the shorter the wavelength, the smaller the angle of deviation. And the dispersion pattern spectrum for diffraction grating is shown as below. So notice it's completely opposite to refraction because you see the violet diffracts the least and red diffracts the most. And of course, in reality, these would overlap. But in terms of diffraction and refraction, you notice it's the opposite order, right? Red to violet, refracting the least, refracting the most for violet. And then for diffraction, violet diffracting the least and red diffracting the most. Note, it says if light is monochromatic, one wavelength of light, then you'd see only the wavelength on the screen. This would give a pattern like Young's double-slit experiment. So the shorter the wavelength, the smaller the angle of deviation for diffraction. All right, polarization of light. So when a wave travels through a filter that allows vibrations only in one plane, then the resulting wave that is produced will vibrate in that plane only. We call this light polarized. For example, imagine a rope that's moved up and down and then is moved side to side. If the rope passes through a vertical slit, then only the vertical waves will pass through. The side-to-side waves would be absorbed or reflected. If these vertically polarized waves were then passed through a second slit that is horizontal, then the waves cannot pass through at all. They would be completely absorbed or reflected, and the transmission would almost be entirely stopped. So notice the vertical slit, only the waves that are vertical pass through, and then meet a horizontal slit. Nothing transmits, nothing moves through. Light waves radiate in all directions, and this light is referred to as unpolarized. Much like the rope, when it goes through a horizontal polarizing filter, it is plane polarized. Specifically, in this case, it is horizontally polarized, which means it oscillates entirely only on one plane. If it then goes through a vertical polarizing filter, cross-polarized, then the light energy is almost completely absorbed, so near zero intensity. Light can also be partially plane polarized when it reflects off of a surface or refracts into a new medium. Of course, the polarizing filters are shown here. You can see it if you take a look at the light intensity going through. As you rotate the filter, you notice that you get a change in light intensity. And so when we have the two filters crossed, as I rotate this further and further, you notice no light gets through whatsoever. Okay? And when the slits are parallel to each other, then light is transmitted. Okay? All right, it says applications of polarization. Polarizing filters are used in cameras and sunglasses to remove some of the light that reflects off of surfaces or refracts, scatters through the atmosphere, which has been partially plane polarized. That's to reduce some glare. LCD displays and digital watches and calculators have polarizing film within them. Millions of microscopic crystals float between electrodes. When the electrodes are charged, the electric field created causes the crystals to line up, cross-polarized with the film. This results in dark areas since the light cannot exit, which is seen as numbers and text. Many insects, such as bees, use polarized light for navigation since it is always perpendicular to the direction of the sun. And radio waves transmitted from towers are typically polarized, defined by the orientation of the electric field. AM and FM are vertically polarized, while television is horizontally polarized. All right, that essentially sums up the notes here. Let's take a look at some questions. We'll start these ones on the next little section, okay?